So folks, in this question, which is question number 49 in the textbook, which corresponds to number 9 in our homework set, we're asked to compute the torque in a bolt. So hopefully we saw, as we worked through these problems up to this point, that the torque is equal to the lever arm, which we usually write as the vector r, crossed with, and I guess that's a vector too, crossed with the force vector that's being applied to it. So just so you know, this letter right here, that's the Greek letter tau, that's what we use for torque. Usually it's implied because it's torque, we don't need to put a line over the top, we know it's a vector. But this is our radial arm, and we're going to cross it with the force that we're applying to it, and that's going to generate the torque. You should think of that as if you took a hex head bolt and you then fixed a crescent wrench to it, so I'm trying to draw a crescent wrench there that you're applying to that bolt, and you got some sort of lever arm here, so we call this the lever arm R, and you're going to apply some sort of force vector to it, that if you want to figure out how much of a this is going to end up rotating the bolt, if you want to figure out how much rotational force you have, and remember that rotational force is either going to be coming, so if we're looking at this as the XY coordinate system, then we would imagine the torque as coming either out of the board or into the board. So this is either going to generate a force that's going to drive the bolt outwards or inwards to whatever object it's affixed to. So that's what we think of as torque. But as far as the mathematics is concerned, all we need to do is compute this particular cross product. So in our problem here, what we have is we've got maybe a, do they say bolt again? Yeah, so we've got a bolt sitting at the center of the XY coordinate system. So there's our bolt, and we've got some wrench that we're applying to it, and we imagine that this wrench is 1/4 of a meter long. So stripping the pardon the pun, but stripping down the information here to where we just have a point, this would be the bolt, and we would have this radial vector right here that we'll label as R, and R in this case would be the vector, based on how I drew this would be the vector 1/4, 0, because that's 0.25 meters. So we're going to go ahead and then apply to this wrench a force of 60 newtons, and it's going to be applied at 135 degree angle to the wrench. So we imagine, if you were to extend this outwards, you could create a angle centered right here, and so 135 degrees would be, if we put another little coordinate system here, would be in that third quadrant. So if we go ahead and draw the force that we're applying to it, that would be our force that we're applying to that wrench there, where that angle is 135 degrees, and the magnitude of that force vector, we're told, is 60 newtons. So we've got a oops, and I should be a little more careful here, folks. This is in 3 dimensions, and so this radial vector should be 1/4, 0, 0, because it's also in the z plane there. So it's only extending outward along the x-axis. This needs, of course, to do a cross product, this needs to have 3 components. So we could go ahead, we weren't given the 3 components of the force vector, but we could go ahead and compute those if we wanted to, component-wise. So let's go ahead and do that. Even though we don't have to do that for this problem, I think it makes more sense to put in context of something we have solved first. So if we were to compute these component-wise, the x component we notice is going to be negative, right? So that's going to be 60 times the cosine of 135 degrees, and then we will have 60 times the sine of 135 degrees for the y component, and the z component, which, remember, for this we're thinking of the z-axis as coming this way out of the plane. The positive z-axis is coming out of the plane there. That component's going to be 0, because this is all, the 2 vectors lie within the xy plane, although the torque is going to be perpendicular to both of those, so that's going to be pointing in either the positive or negative z direction. So we could take this a step further, because that would be the square root of 2 over 2, so this comes out to be 30 square root of 2, 30 square root of 2, comma 0, that's our force vector. So if we wanted to compute the torque, what I'm saying here is what we could do to compute the torque is we could say that the torque is equal to the cross product of our lever arm, which is 1/4, 0, 0, and we would cross that then with our force vector of 30 square root of 2, 30 square root of 2, and oops, careful folks, this should be a minus. I dropped that minus sign, I knew I was going to, and 0, and we could actually compute this cross product the way we have been. So I'll set that up just as a reminder. The way we've been showing how to compute that cross product is as I, J, K, and then we would take 1/4, 0, 0, and then we would take minus 30 square root of 2, 30 square root of 2, and 0, and we could go ahead and compute that 3 by 3 determinant as we have. And that would be a fine way. Once we'd have that, we'd have some sort of vector sitting in R3. And in fact, we know just based on how the cross product works that these first two components are going to be 0, and it's only going to be a third component. And we should see that because if you apply the right-hand rule to these two vectors right here, if you took and transposed this over here, you would expect the cross product to be either pointing outwards or inwards, depending on how those values work, along the z-axis. So we'd expect the x component to be 0, the y component to be 0, and then we'd have to figure out what that z component is. Then to answer the question, we would just simply take the magnitude of that torque vector. So that's a really long explanation for sort of the full way of doing this problem without noticing any other useful ideas. You would go ahead and give these two vectors. There's the r vector, there's the force vector, and you cross the two together, and that gives you the torque vector. And we know how to do all of those tasks, and then you could just compute the magnitude of that. But I think there's a better way to do this problem, and we hopefully saw this as we were working through the earlier questions in this homework, and that is, if all we want to know is the magnitude of the torque vector, which is what we're asked here, we're asked to find the magnitude of r cross f, that we can compute this by simply taking the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between those two vectors, and we know that the angle between these two vectors is 135 degrees. Now careful there folks, just to make sure that's clear, what we would do is to represent that is, here's our coordinate system, and here was our radial vector, and then here is our force vector, and the angle between those two is that 135 degrees. And so we can go ahead and compute this because we know that the magnitude of r is just a quarter because its other two components were 0, right? This component's a quarter, those two. So how long is this vector? It's got a length of a quarter. We were given explicitly that the force vector had a magnitude of 60 newtons, and we know the angle between them. We were given that the angle between them was 135 degrees. So folks, that whole first 7 minutes of this video really weren't necessary to answer just this part of the question, where to find the magnitude of the torque, we're just going to take 1/4 times 60 times the sine of 135 degrees. And if we compute that, we would have, let's see here, that would be 15 times the square root of 2 over 2, and then torque is measured in Newton meters. So we could go ahead and enter that into my math lab. So let's do that. So I pulled that up. Here's our question. We could go ahead and enter in the magnitude and the units. And so we said that that would be 15 square root of 2, and all of that. Let's see here. Let's do it like this. So we've got 15 square root of 2, all divided by 2, and then our units there, we want the Newton meters. And there we have the solution to this. Folks, I hope this was helpful, and let me know if you have any questions on this. Thank you very much.